Good afternoon. My name is Oleksandr Khasai, postgraduate student of Bogolyubov Institute for Theoretical Physics. And in my oral talk, I would like to tell you about neutrino extension of the standard model, and in particular, constraints on the parameters of the neutrino extension of the standard model. We all know about the importance of the standard model and its great contribution to the particle physics, but it's still not complete, and it cannot explain such phenomena as, for example, neutrino oscillations, dark matter, or baryonic asymmetry of the early universe. In this work, we considered the minimal neutrino extension of the standard model, which consists of addition of three right-handed sterile neutrinos. And theoretically, such a model can explain all the mentioned phenomena. The lightest sterile neutrino contribution to the baryon asymmetry is negligible in such a model, and its lifespan is estimated to be extremely long. And as such, a consequence of this, we can safely focus on the two heaviest right-handed neutrinos. The Lagrangian parameters are bounded from below by the baryon asymmetry of the early universe and bound from above by the fact that sterile neutrinos have not yet been found on the collider experiments. Okay. The two heaviest right-handed neutrinos are responsible for baryon asymmetry, so we can consider a model with only two right-handed neutrinos. The values observed in experiments look like this, like S alpha beta and R alpha beta. And they are limited by quantum corrections to processes that are allowed in standard model and corrections that generate processes that are forbidden in the standard model. Upper bounds on the quantities from present and future experiments are presented in Cohen-Frigerius paper, and you can see them on this slide. As a next step, we wanted to express our observables in terms of the masses of active neutrinos and sterile neutrinos, and the quantity U total squared, which is constructed from the mixing angles between active and sterile neutrinos. Looking at this formula, we can conclude that because the difference between the masses of active neutrinos and sterile neutrinos is extremely huge, and because mixing angles between active and sterile neutrinos are finite, we can safely conclude that this quantity hyperbolic cosinus is extremely large, and we can conclude that in general such approximation as hyperbolic cosinus equals to hyperbolic sinus. And later in our work we used this approximation. And for the mentioned above purpose of wanting to express our observables in terms of these parameters, we used a very convenient Khasai parameterization, which is presented here on screen. And here, omega here is that the omega which was mentioned on the previous slide. It's a parameter of this Khasai parameterization. Okay. But this Khasai parameterization can sometimes be way too cumbersome for analytical calculations, and so we introduced a new matrix X to simplify our computations. Using this modified parameterization, we can rewrite our observables in simple forms. Forms for S alpha beta for normal ordering of neutrino masses are presented on this slide. Using this approximation that hyperbolic cosinus is equal to hyperbolic sinus, we can obtain the following relations between observables, and they will be valid for different masses of sterile neutrinos and non-zero masses of active neutrinos. Similar relation as written above have been obtained in the work of Cohen and Frigerio, mentioned here, but in their model, they had active neutrinos with zero masses. And I would also like to note that in their model, all the quantities S alpha beta and R alpha beta are real. But in our work, we showed that these quantities are complex. Quantities S alpha beta and R alpha beta are generally complex with non-trivial complex phases. Okay, and using these relations which we obtained, we were able to improve certain experimental constraints on the observables as presented on the slide. Using our parameterization and substituting all known quantities from the particle data group, we obtained the following expressions for our observables. Having found the minimum of the trigonometric functions, we were able to find the upper bounds on the given quantities, and hence the forbidden regions for the neutrino masses and quantities and quantity U total square. Here on the presented graphs, we can see a comparison between the results of our work, which are pink and purple lines, with the results of the work of Oleg Ruchayskiy, which is mentioned here. As we can see, our relatively simple model reproduces well the past results of the present and future experiments, even for much more complex models. Okay. From Shaposhnikov and Asaka's work, we know the expression for the baryon symmetry of the universe. Using this expression, we can express the baryon symmetry in terms of our observables, as we did here. If we tried using a relation between observables obtained in our work, we would have obtained an unreasonable result, as seen here. But if we consider our situation more carefully, we can see that this result is caused by the previous approximation, that the hyperbolic cosinus is equal to hyperbolic sinus. And if we consider that such approximation is no longer valid, and we'll calculate and we'll make calculations with this in mind, we will be able to obtain much more sensible results, as we did here. Like the problem The problem here is that this quantity that we use to express baryon asymmetry with is extremely small, and using this approximation that which previously very this approximation is generally extremely safe because really difference between masses of active and sterile neutrinos is extremely huge, but this quantity is so small that if we didn't take into account this difference, we will obtain such an absurd result. So by taking it into account, we were able to get correct and sensible results. Okay, and after the transformations, we obtained the new expressions for the baryon asymmetry in terms of our observables, as presented on the slide. From known experimental values for baryon asymmetry, it's easy to get constraints from below on our observables, and comparing it to the comparing it to the experimental constraints from above, presented here, we can see a huge disparity. And this disparity suggests that baryon asymmetry is an unsuitable parameter for calibrating neutrino models. So we can't get a very useful information from baryon asymmetry to calibrate some parameters in neutrino models as is shown here, because the difference between upper bound and lower bound is extremely huge. So it's like the range for parameters is quite high. So we can't get anything from here. And in conclusion, we obtained new expressions between observable parameters of neutrino extension of the standard model for our case with two heavy right-handed neutrinos of different masses and active neutrinos with different masses, presented here. Using this expression, we were able to improve experimental constraints for observables S alpha beta. We obtained a new expression for baryon asymmetry using our observables. We have shown that the upper bound on the observable parameters from the non-observation of forbidden processes in the standard model and the lower bound from the baryon asymmetry differ by many orders of magnitude, and thus showed the unsuitability of baryon asymmetry for calibrating neutrino models. Thank you very much for your attention.
Thank you very much. We have time for several questions, if any, please.
Can you have a question about the experimental results? You told that they align with already existing result, but you also told something about that your model aligns with the future experimental results. Can you explain what do you mean by that?
Okay, give me a second. What I mean by future experimental results is in the future experiments, there are like expected upper bounds on the observable parameters. Like we expect that in the future experiments, we will be able to obtain such constraints as presented, for example, in this table. Like second column is tells us about the constraints that we already have, and third column talks about the constraints we expect to we expect to see. So I by showing the future experiments, I meant that it is expected.
Okay, thank you. Are there any other questions?
I have.
Yeah, please.
Okay. What is a very important point? They introduce crucial modification standard model. In this standard model, you use the one scalar field. What is possible in the one scalar field? Explain three very important problems. Do you understand or not?
In this model, we introduced three sterile neutrinos, and first of all, neutrino oscillation is just by the fact that there are like there are right-handed neutrinos, we can explain a neutrino oscillation. Then of these three sterile neutrinos, we have one that is relatively light and two that are relatively heavy. And those two that are, the first that is relatively light, it is a candidate for a dark matter particle. Like it is not a part of my work. No, it's not directly a part of my work, but in general, in such models, this relatively light particle is a candidate for dark matter with some really huge lifetime, and the rest two heavy particles, two heavy sterile neutrinos, they contribute to the baryon symmetry.
You only mentioned that these sterile neutrinos are very heavy, but what are the typical mass you expect or you consider?
Okay, for the light particle, it's about something like a few kevs, maybe tens of kevs. And for two huge particles, it's about maybe 100 of GeVs, something like this. About heavy particles, it's like not really that known. In this work,
I mean this sterile neutrinos. They have mass 100 GeVs.
It's it's a possible mass. Like a part of this work, at first, in the very beginning, when we tried.
But I think the picture is very different. Either that 100 GeV or 1 MeV, yes. Million times smaller. It is also possible. I don't understand. Sterile neutrino mass can be any value from very small but larger than real neutrinos, up to 100 GeV or 1000 GeV, I don't know.
GeV maybe.
And the answer will be very different depending on this mass.
So, that's part of the model of the neutrino of this neutrino model. That in theory, if we get the masses correctly, we can simultaneously explain all those three problems that we try to make this
Okay, thank you.
to give this
Unfortunately,
masses
we have no time for
such
long
values that
discussion.
they can
I
explain.
don't understand, but we have no time for discussion.